We are going to prove now the Bolzano Weirstrass theorem. This theorem says that for every bounded infinite set of real numbers, there will be an accumulation point. Okay, that means that if you have your set in between two bounds, okay, and it's an infinite set, and you start trying to put your numbers as far away from each other as possible, at some point you are going to run out of space and it will have to accumulate somewhere. Okay, just because of the fact that it's infinite. The set is infinite. Okay. Now, the proof is similar to what we did for the Hein-Borel theorem. Okay, what we are going to do again is to show that there is a clever set P and then use the least upper bound property of the real numbers. So let's give number names here. So let's say that S is an infinite set in R bounded above by B. Okay, and also because it's bounded also from below by A. As I said, now we are going to define a clever set that is the set P. Okay, how do we define this set? Is the set of the real numbers Z, okay, real numbers in R, not, for now S is not involved, okay, such that there are only a finite number of points. When I say a finite number of points, I mean a finite number or none of them at all, okay, of the set S that are less or equal than Z. Okay, and you see here is where the set S comes in. Okay. Now, what do we need to show here? We need to show here the first thing is that P has a least upper bound. Let's call it lambda. And the second thing we want to show is that this lambda is an accumulation point for S. So let's start with the first point. Let's keep our P in view. So let's show one that P has a least upper bound lambda. Now, notice because of the way it's defined, A belongs to P. Okay, this is true because no element of S can be less than the lower bounds of S. Okay, so this means that P is non-empty. But now, P is bounded above by B. Okay, remember B is an upper bound for our infinite set S. Okay, this is true because the infinite number of elements of S are less than or equal any upper bound of S. Okay, because of these two, because it's not empty and it's bounded above by B, there exists lambda that is a least upper bound. There we go. Okay, so we can move on to point 2. Prove that lambda is an accumulation point for S. Okay, so here, what is the definition? We need to show, remember that for every neighborhood of lambda, okay, let's call it U, there exists at least one point in S such that S is in the neighborhood, S is in U, and S is not lambda. Okay, so if we want to write this down in terms of intervals, what this means is that we need to show that there exists S in the capital S set such that the distance between lambda and S, okay, which is given by the absolute value of the difference, is less than a number epsilon small and is still positive, okay? Let's say this is for some small epsilon, okay? We use this letter epsilon always when we mean a small quantity. All right. So there are two cases here. Two things can happen. The first case is that this lambda belongs to P. And guess what? The second is that lambda does not belong to P. Okay, so we are going to cover all the cases. Now, let's put the second case a little aside. So what happens if lambda belongs to P? In this case, lambda plus epsilon cannot belong to P, okay, because lambda is a least upper bound of P, okay? So by definition of the set P, this means that there exists an infinite number of an infinite number of elements of S that are less than lambda plus epsilon. Okay, so how does this look? So we have here our lambda, which is in P, and our lambda plus epsilon, which is not in P. Okay, so being in P means that there are just a finite number of elements in S that are smaller than lambda. Okay, but not being in P means that there are infinitely many numbers that are numbers in S that are smaller than lambda plus epsilon. So if here there are finally many, and here there are infinitely many, guess what? There are infinitely many numbers in between lambda and lambda plus epsilon. There have to be. Okay, but that means we didn't need infinitely many. What we needed was one. Okay, so our conclusion here is that there exists at least one element S in S, okay, between lambda and lambda plus epsilon. Okay, and then this means that it is true what we were saying, that S minus lambda in absolute value is in between 0 and epsilon, and therefore lambda is an accumulation point of S. Okay, so this is the first case. Now the second case is when lambda is not in P. Okay, and because lambda is a least upper bound of P. Okay, and we know, of course, lambda minus epsilon is smaller than lambda. This means that there exists some point P in the set capital P such that lambda minus epsilon is smaller than P, smaller than lambda. Now, if you don't see this right away, this may require proof. So I just think what happens if this didn't happen. Okay, if this didn't happen, that means that we should be able to decrease lambda. Okay, that lambda was actually not the least upper bound, that we would be able to find a smaller bound than lambda. Okay, so that cannot be, so that's the argument. But now, because we have, notice what happens here, we have our P that is in capital P, we have our lambda that is not in P, and we have our lambda minus epsilon that we don't care. What do we have here? It's a similar situation to before. We have our P, we have our lambda, and we have our lambda minus epsilon. Let's put it somewhere here. Okay. And we know that there are infinitely many points, okay, because this doesn't belong to P. There are infinitely many points of S, but then because P belongs to P, you have finitely many that are smaller than P. So again, what happens is that we are going to have an accumulation here. Okay, because here we just had a few, but here we must have infinitely many, so they will accumulate. Okay, but in particular, we don't need those many. We just finish as before. We say, well, okay, there exists some S in S, okay, such that S, well, P less than S less than lambda. And therefore, the distance between S and lambda, okay, you can see it in the picture, the distance between our S that is somewhere here and lambda is got to be less than epsilon and bigger than 0. Okay, and that's it. This is what we wanted to prove. We get the same conclusion as before, and with this we conclude the proof of the Bolzano Weirstrass theorem.